By the end of all this work, we will know what all of our subsystems are, what each of those subsystems needs to be able to do, and how each of those subsystems interface or relate with one another. It's now time to make some design decisions. When we look at each of the subsystems in our system, we need to make some decisions about how we are going to proceed in order to realise them. Broadly speaking, we have three options. In some cases, we may be able to go straight to the market and purchase the subsystem off the shelf. Sometimes an off-the-shelf option needs to be modified in some way before being suitable, and in other cases there are no off-the-shelf solutions and we need to develop a solution from scratch. Let's start by looking at the off-the-shelf option. Using our car example from earlier, if the engine was a subsystem within our car design and we knew exactly what that engine needed to be able to do from a function and performance and interface perspective, chances are there would be some commercially available engines that would fit the bill. Commercially available subsystems offer us a number of advantages. They're likely to be known in terms of their function and performance. That is, there's likely to be some objective evidence in existence that the subsystem does in fact perform in accordance with the claimed performance. Off-the-shelf items are likely to be immediately available or available with some known lead time, making planning much easier. Their costs are also going to be a known quantity. Thinking life cycle for a minute, they are likely to have an existing support system associated with them, including tooling, test equipment, spares, training, maintenance support, and so on. These are all advantages to the off-the-shelf solution. However, there are some things to think about. The technical documentation associated with off-the-shelf systems is, in my experience, something to look out for. If we're going to use off-the-shelf subsystems, we must have access to appropriate levels of technical detail to allow us to integrate the subsystems, test and operate them, and train people in their use. If the documentation is unsatisfactory, then this must be considered when making the design decision. We also need to watch out for obsolescence. We need to take into account the stability of the technology that's used in the off-the-shelf item and the market size enjoyed by that technology. It's quite possible, in fact I've experienced it, for off-the-shelf subsystems to become unsupportable if they become obsolete or if the commercial market disappears for some reason. In some cases we come across an off-the-shelf option that's almost suitable for consideration but lacks one or two key attributes. If an off-the-shelf option is close to meeting our requirements, it might be possible to consider using the off-the-shelf option and developing a modification to make it more suitable. Modified off-the-shelf items have many of the same advantages as pure off-the-shelf options, but we need to be careful about a few things like warranty and support agreements. Making changes to an item after it has been procured may render these agreements invalid. If we are going to modify an item, we will need to consider the modification to be a detailed design task and we'll need to develop the modification in a controlled manner. We're going to discuss detailed design in the next section. One other point to note about modifying off-the-shelf items. In my experience, people tend to drastically underestimate the effort associated with modifying off-the-shelf items for some reason. They also tend to assume that critical enablers, like detailed design data for the item, will be available. The point I'm trying to make is you must be careful not to underestimate how much time, money and effort will be involved, and you must ensure that critical enablers, like detailed design data, is available prior to making decisions about modifying off-the-shelf items. If there are no off-the-shelf items available to us, we may need to consider designing and developing the subsystem from the ground up. Naturally, this will be an involved process, which we'll discuss soon, but remember also that we'll need to think about life cycle issues and ensure that we establish through-life support for anything that we design from scratch. Systems engineers need to work closely with our integrated logistics support colleagues during this period to ensure that our design is manufacturable, supportable and disposable. More on that later. A key advantage for the developmental approach is that theoretically we should end up with a perfect match to our requirements. Unfortunately, I've got some bad news about that. Another observation from my experience is that sometimes people reject an off-the-shelf option that's not quite perfect and go down the developmental path. After a long time and a lot of money, they end up with a developmental solution that's further away from perfect than the off-the-shelf option that they rejected a long time before. Apart from the function and performance shortfall, it would have taken them a long time and a lot of money to find that out. So please, be sure that the developmental approach is definitely the way to go before going down that path. When we're looking at our subsystem design, it's rare that we happen upon the best answer straight away when it comes to how to design our subsystems. We need to make sure that our subsystems are going to perform in accordance with the requirements that have been allocated to them, but we also have to make sure that when all of those subsystems are plugged together, we end up with a system that meets all of the system level requirements. We need to explore and exploit any room to move with respect to our subsystems so that we arrive at the very best possible answer. Sometimes this process is referred to as making optimal use of any design space that's available to us. Please note carefully that just because I'm going to call this design space does not mean that the concept is applied only to trade-offs involving physical space. The space I'm talking about is room to move. It might relate to bandwidth in a communication system, processing power in a real-time computing system, electrical power, physical space, weight, and so on. It's not always physical space. Let's go back to the car and the air conditioner to illustrate the point. Let's say the weight of the car needs to be no greater than 1,225 kilograms. This may be a system level requirement in the form of a constraint. During preliminary design, the systems engineers make some design decisions about how much of this 1,225 kilos each of the subsystems will be given. For example, we might allocate 200 kilos to the engine, 25 kilos to the air conditioner, and 1,000 kilos distributed amongst the rest of the subsystems. There will be other system level constraints assigned to these two subsystems, such as physical size constraints, but for this example, the weight constraint is enough. Naturally, the engine will have a whole lot of other system level requirements allocated to it that will result in derived requirements. For example, a derived requirement for the engine might specify how much power the engine needs to be capable of delivering to power the car, but also to power other subsystems like the air conditioner. Similarly, the air conditioner will have other requirements allocated to it, such as how much power it's allowed to consume in keeping the car at a certain temperature under certain environmental conditions. If we give the air conditioning experts all of their requirements, and we give the engine experts all of their requirements, and just leave them to it, they'll end up developing their own subsystems independently of each other. The air conditioning people will come up with a great design that's able to use all of the available power and weight allocated to them to create an air conditioner design that meets or exceeds their requirements. The engine people will do their best to do the same. This sounds good because we'll end up with a car that meets its air conditioning requirements and its engine requirements, as well as the overall weight requirement. But what if the engine designers are struggling? They might be able to build an engine that meets all of the requirements, but it's a little bit too heavy, or it fails to deliver quite enough power. It would not make sense from a system point of view to allow this to happen if the air conditioning team were able to meet all of their requirements with room to spare. Consider, for example, if the air conditioner could be designed to be slightly lighter than the allocated 25 kilos and still meet all of its requirements. If the air conditioner could be designed to be only 20 kilos, the systems engineer could allocate the spare 5 kilos to the engine team and allow them to design an engine that is now 205 kilos. Overall, the car will still weigh 1,225 kilos, but we will end up with an adequate air conditioner and an adequate engine in the process. What if the air conditioner could be designed not only to be a little bit lighter, but could also be designed to consume a little bit less power from the engine than initially thought? Now the engine does not need to produce as much power as previously and can weigh 205 kilos. By using some of the design space available from the air conditioner, we have given the engine designers much needed room to move. What we'll end up with is an adequate air conditioner and an adequate engine that, when integrated together, are able to deliver the required system-level performance. If we're not careful though, we could have ended up with a fantastic air conditioner coupled with a marginally compliant engine which integrated together to deliver a car that was underpowered and overweight. As I've said before, in systems engineering, we would much prefer to deliver a system that meets all of its requirements rather than a system that exceeds some requirements and fails others. To do this, we simply must keep an eye on any design space available to us and make sure we are making the best use of that space. Eventually, after a lot of work, we'll have decided what all the subsystems are, what they need to do, how they will interrelate with each other, and how we will go about designing them. We will also be able to show how the subsystem design contributes to and supports system-level requirements. We will have thoroughly explored design options and any available design space. We'll document all of this information in the form of subsystem specifications and design decisions and rationales. Once this has been completed, we're going to stop, draw some breath, and have a design review. This design review is normally called the Preliminary Design Review, or simply PDR. At this design review, we're going to look at all of this information and confirm that we're ready to proceed to detailed design. We'll also ask the decision makers to justify some of their decisions by asking some simple questions like, when you came up with this option, what other options did you look at? What are the relative merits of the different options? Have you considered life cycle issues like manufacturability, maintainability, and disposability when making your decisions? These are all good questions that are simply looking to confirm that the design decisions made during preliminary design are robust and defendable decisions. After all, we're spending a lot of time and effort on this exercise, and we want to make sure, as best we can, that we're going to end up with the best possible solution. Once the design review is complete for each of the subsystems, we can then move on to detailed design. From our preliminary design review, we have confirmed decisions about how each of the subsystems will be realised. As you'll recall, some will be procured off the shelf, others will be modified in some way, and others still will be designed from scratch. The subsystems that need to be modified or developed from the ground up will need to go through the detailed design process. Even those subsystems that are procured off the shelf will need to be integrated to form the system. That integration effort is also part of the detailed design process. At the end of the detailed design process, we will need to be certain that we have a design that meets all of the system level requirements set by our stakeholders and can be manufactured, produced and constructed and can be supported or sustained throughout its operational life. We'll also need to confirm that the system can be disposed of when the life cycle comes to an end. We have a lot of work to do. If we consider that the next phase in our life cycle is the production and construction phase, we get a hint as to what needs to be done during detailed design and development. If we're dealing with hardware, which is defined here as anything that's not purely software, we have to come up with a detailed design of the subsystem, but we also need to be able to specify how it's going to be built. This description includes parts lists, materials descriptions and specifications, and construction and production processes. After all, the parts, materials, and construction process will impact heavily on the function and performance of the subsystem, and therefore needs to be carefully considered, designed, and specified. Detailed design is a tough job, and it's the job that's traditionally associated with professional engineers. Professional engineers are expected to be able to take a specification and determine a solution that meets those requirements. We're not going to cover professional engineering here, but it's important to emphasise that detailed design is an iterative process. Very few engineers are lucky enough to come up with a perfect solution the first time. We end up designing, building, testing, learning, repeating until we're happy with the process. We do this over and over again until we're satisfied with the result. Professional engineers will use plenty of tools to help them do this. Some of the common tools that you might find include prototyping, modelling, simulation, and reusing similar designs that have worked before. For example, consider that we're going to try to come up with a detailed design for our kitchen. It's highly unlikely that this design will be done purely on paper. We'll need to consider the workflow in the kitchen so that the kitchen works as a kitchen. For example, we don't want to put the fridge on the opposite side of the kitchen from where we prepare food. We would not want to put the dishwasher a long way from where we store our cutlery and crockery. We need to consider where services from other subsystems like cold water, hot water, gas, drainage and power can be provided. Should the kitchen constrain the design of the electrical and plumbing subsystems, or should the kitchen be constrained? In all likelihood, it'll be a bit of both, but these are the sorts of things we need to be thinking about during detailed design. Coming back to the kitchen, I think we'll probably go out and have a look at kitchens in showrooms and display homes and see what they look like. We'll probably make use of software tools to produce layout drawings and explore things like workflow. We'll probably want to select major components in the kitchen like stoves, ovens, sinks, dishwashers and so on. We'll go through this process for all of our subsystems in our design and confirm that the integration of all of the subsystems is going to work for us at the system level. Once we've completed this process and documented the results, we're ready to go to the final review prior to construction and production. We're going to call this review the Critical Design Review, or CDR. The role of CDR is to confirm that the detailed design is complete and has been appropriately documented. We will ask very similar questions to what we asked at PDR, albeit at a different level. We will be looking for evidence that the design process has been rigorous, and we'll be looking for consideration of things like design alternatives, selection of preferred approaches for sound reasons, solid documentation discipline, and clear readiness for the construction and production process.
If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.